All right, so I want to go over a couple of limit examples just to demonstrate how to use all those limit properties. Now, I know that we have already established that polynomials are continuous, and so if you have a function which is continuous, then you can apply direct substitution when trying to evaluate a limit. So when doing like a problem on a test or something, you're not going to have to go through all the details that I'm about to show you for a problem like this, right? That's a polynomial, so we can like just evaluate this at 2, and that will be the limit value. But I want to just use this as a nice basic example to demonstrate all these properties that I've been showing you, because these properties are useful occasionally in sort of the non-continuous cases when things aren't so simple that you can just evaluate. So this is just to demonstrate how they work. So suppose we just don't know that we can apply direct substitution to this problem. Well, then what we do know is that this is a sum, right? This polynomial is a sum of 3 terms. And we know that limits distribute across sums, right? That the sum of limits is the limit of the sums. So we can rewrite this as the limit of x squared, and then plus the limit of 3x, and then plus the limit of 5. So that's by the sum rule. We have the sum and difference properties, which we introduced earlier. So then, let's see, then we know that if we have a power function, like here, if we have a limit of a power function, then we can take that limit and stick it inside the power function. So we can say, right here, this is going to become, we're going to take the limit of just x and then square that, right? So that's taking the limit and sticking it inside the squaring function there. All right, that was one of our properties. Another property is the constant multiple rule, which would be saying that if we have a multiple of a function, we can take that multiple and pull it outside the limit. So this multiple of 3 is going to come outside. We're going to have 3 times the limit of x. And we do have a rule for dealing with constants, but let's get to that in just a moment. So in this step, I've applied the rule for dealing with powers and the constant multiple rule. Then what we have left over in here, we grab a red pen. What we have right here is one of the basic limits. That's the limit of x, right? And here's another instance of that. And here's another basic limit, which is the limit of a constant. So now we can apply those really basic rules that the limit as x approaches 2 of x is 2. Right, and that'll be the case here as well. And then here, the limit as x approaches 2 of 5, well, it doesn't matter what x is approaching. 5 is approaching 5, no matter what, because it's constant. It's just staying where it's at that value. So that's just going to be plus 5. And now we can evaluate that. Let's see, it's going to be 4 plus 6 plus 5. It'll be 15. So that is this, by the way, is this is a much more rigorous approach to evaluating limits than just graphing it and testing some points, or sort of using a numerical approach. If I like on the worksheet, there's problems where I ask you to solve limits analytically. I want you to be using properties like this, but you're also allowed to use whenever you encounter a continuous function, you can use direct substitution on that. So yeah, so let's see. Second example, I want to do one that involves composition. We'll let x approach 2 again. I don't know, not that it really needs to be different or the same. It's just I'm going with x approaching 2 just for the sake of demonstration here. So here is a composition of functions. We have an exponential function here, and inside that exponential function we have stuck in there a rational function. So as x approaches 2, well, the rational function, the denominator is not going to be 0, so that means that 2 is in the domain of that rational function. And that means that it's going to be continuous at 2, so we can evaluate the limit of the rational function by just applying direct substitution. And then the fact that our outer function in this composition is the natural exponential, that is a continuous function, so we should be able to apply that rule in the previous video about function composition, where you stick the limit inside. We can apply that. So my first step is going to be to take this limit and put it inside the inner function. Well, what does that look like in this case? It means instead of doing the limit of e to the power blah blah blah, we're going to do e to the power limit of x squared plus 5 over 2x minus 1. That. So you can see the limit is now being applied just to the inner function in this composition, and then that limit value, whatever it is going to be the exponent of this e, right? So now we just need to evaluate that limit. Now I hope that limit will exist, but it should, because 2 is in the domain of that rational function. So we should be able to do that with direct substitution. We're going to have 2 squared plus 5 all over 2 times 2 minus 1. Now, as you can see, well, I guess I should actually evaluate that. I think that evaluates to 3. So this is going to be e cubed, which I just write it as e cubed. I wouldn't try to get a decimal version of that, because then we'd have to truncate that decimal somewhere or round it or something, and that would not be exact. So I prefer exact solutions. Yeah, so there we go. So I think that'll pretty much do it for some limit examples. I know that the result of this second one was that we did end up just doing direct substitution straight from the beginning, but we justified that a little more appropriately by the combination of 2 theorems. First, using the rule for dealing with composition, and then using what we know about rational functions and their continuity. So while it did end up just being a direct sub, and it feels like we could have done that in one step, we justified that a little more rigorously by doing a few steps in between.